In this session, we want to look at creating a truth table for that master-slave flip-flop. So I'll come back here to Circuitverse, and here was our flip-flop. I'll come over to diagrams.net, and I'm going to start with the truth table we had for the enabled NAND latch. Copy that, bring that down here. And so the first thing is that this will be a NAND master-slave flip-flop. And one thing I didn't do on the circuit that I should do is we did discover that the outputs could only change on a transition of the enable. Okay? So what we've seen up to this point was that as long as the inputs were in a certain state, the output remained consistent, and if we had some feedback like we do in the latch, we might need to know what they were previously. But again, as long as the inputs were in a state, the outputs were in a given state. What we found now is the only time it could change is on a transition of the state of an input, like the enable. So what I'll do is, instead of calling that enable, I'm going to transition to calling that a clock. Okay? It's this idea of we've got much more precise timing now. So again, we'll call it a clock instead of an enable. Okay, great. Back over here in my truth table then, I'm going to change this and abbreviate to CLK for clock. We do that commonly. I have my set and my reset. And so what we're finding then is that as long as the clock is in a 0 state, it doesn't matter what S and R are, and the output is latched, or remembering what it was. And as long as the clock is at a 1, the inputs don't matter either now, okay? And it's in the memory state. So what we find is there's only a transition to worry about. So I'm going to grab another line here, and I'm going to zoom in a bit and make a symbol to indicate the transition occurring. Okay, so I'm indicating that's going from a high or a 1 or a preferred state to the lower state. And it's when that happens is when I can set or reset. So I'll move that up there, bump it up a little bit, copy that, paste another one here, and there we go. Now, there is a little bit of weirdness here. What about the invalid state? It still exists. It may or may not show up in Circuitverse. This is where we're approaching some of the limits of Circuitverse and a digital simulation of this circuit. In an analog world, we would have to be concerned about the propagation delay, the time that it takes a signal to get from the inputs to the output. Okay. It does not happen instantaneously. It happens incredibly fast, but not instantaneously. So if we looked here, we've got 2 NAND gates. We could say there's 2 propagation delays through there. There's one for the inverter. We don't know if they're proportional or not, kind of like that. But all that to say that whether Circuitverse shows you or not, there is the possibility for that invalid state to occur.